Good evening, everyone. My name is Paul Ian Kawasag, and today I'll be talking about the implementation of neural ordinary differential equations. And the reason why I wanted to study this is a lot of times in my data science practice, I've always used neural networks. And the one thing I don't really understand is why. And today we'll try to unravel the underlying principles, both mathematical and practical, of why we should be using this type of neural network, the neural ordinary differential equations. So one motivation for this I can say is with typical neural networks, oftentimes they can fall short to what we can what we typically see is that you often apply these as a black box, and you technically don't even know the mathematical constructs. And from my experience, they're quite less flexible in terms of control without the ability of verifying the solutions a priori. And what I mean by that is that it doesn't allow you to query either stability, convergence, and consistency of algorithms. And oftentimes, you just apply them with a fixed step, an amount of hidden layers and solvers that is not interchangeable in terms of other ways of doing it. And the one method that we're going to introduce here today actually resolves these shortcomings. And with this, we can say that you can use neural ordinary differential equations by allowing for varying depths, hidden layers, and solvers. And oftentimes this is done by specifying a set amount of time steps, sizes, and by accepting an error tolerance. And altogether at the end, we'll kind of give you guys some practical means of implementing this neural ordinary differential equation in terms of a regression and a classification model, with some pretty pictures on some graphical, qualitative, as well as quantitative performance metrics. So without further ado, let's begin. So before we can even talk about what are neural ordinary differential equations, let's kind of motivate this concept mathematically. And one of those ways that this is related to a math construct is the notion of geometric numerical integration. And what I mean by this is that when you're trying to implement a neural network, you oftentimes have to perform a backward and forward propagation. And in the traditional sense, you typically would just use the calculus in terms of a chain rule when you're and you have to apply this multiple times when you're trying to do the backward and forward pass. But in terms of this new type of network, this neural ordinary differential equation, what often is the case is instead of using a discrete system, such as in a typical neural network, such as convolutional or residual neural network, instead it'll be more of a continuous system where we'll be using an optimized function, where instead of actually using a chain rule, we'll be actually using a numerical integration. And I'll kind of clarify this as we go. But what we're trying to cover here is mostly a Hamiltonian system. And with this, using the concepts of geometrical numerical integration, these algorithms allow a preservation of the symplectic structure. And so to motivate the uses of this geometric numerical integration for ordinary differential equations, I can say that it's been utilized in a lot of numerical analysis, especially for numerical differential equations, as well as numerical linear algebra. And why you want to preserve this structure with deep learning is that oftentimes it yields algorithms that are much faster, simpler, and stable, and oftentimes more accurate solutions. And not only that, but by applying this preserved structure, it allows to improve the neural network to make it more robust and yield more qualitatively better results that is not affected by or sensitive to perturbations, which I'll explain in a little bit. And also, there's some tools that can improve the neural network by allowing us to solve really long-time integration systems such as the Hamiltonian, and as well as obtain convergence and a priori, as I mentioned, solution metrics, and allow us to query stability, consistency, such as we'll talk about in a little bit. And altogether, when you're talking about neural networks, you're really stuck to one type of solver, which is the stochastic gradient descent. And once you choose this is used for both the forward and backward propagation, and it doesn't allow you any type of control or to change it either from a forward or backward pass. But using this geometric numerical integration for neural ordinary differential equations, it actually opens up a way for us to use different types of adaptive solvers. And what you're going to find out, which is a really good type of method, is using the Eranga-Kata for solving such ordinary differential equations. So with that, before we can even talk about the neural ordinary differential equations, let's kind of motivate the data science aspect of this. So as I've talked about previously in another setting, I defined what a machine learning construct is and what are the underlying concepts. So mainly machine learning is comprised with supervised and unsupervised learning. Supervised learning is composed of both regression and classification algorithms. And for classification algorithms, the goal is to fit the training data to predict the particular class of the future data. Well, for regression, the goal is to fit the training data to predict a value that has a numerical unit with the future data. And with the unsupervised learning, usually you try to embed the structure of your data set without these future labels. For the focus of today, we're just going to apply supervised learning and using the predictive algorithms of classification and regression. So with that in mind, let's move on to deep learning. So deep learning is just a subset of machine learning, and they can also apply classification and regression. But the main difference with deep learning is it doesn't actually, you don't actually have to manually select feature labels. This can be done by the embedding between the relationship of the input and output from parameterizing the parameters of your network. So in industry, typically, there's been a lot of hype with deep learning, as I mentioned. But now the different tasks that it can range from, you can use it for computer vision, for convolutional neural networks, speech recognition, playing games, reinforced learning, as well as driverless cars and residual neural networks. But with all this advantages, often the case, as I've alluded to it, it really has a lot of disadvantages, such as a way to not being able to track why your solutions are showing what they are, and whether you even have a solution. So often the case is very intractable, and there's no control for the user, and it's kind of serves as a black box system. So what this is specifically is there's really no way for us to query the mathematical constructs of the deep learning. Oftentimes, this deep learning network can solve a lot of problems, but there are no theoretical mathematical concepts that are concretely defined. And in terms of stability, there's no concepts out there that allows us to compute the stability of the training as well as the architecture of the neural network. And if you've worked with deep learning for a while, you're very well versed to knowing that in order to actually get an accurate solution, you need to provide a really deep neural network, which has a lot of layers. In this sense, it becomes a non-convex system, which can easily become unstable. And when you relate this to a traditional neural network, this doesn't. A deep neural network is really not robust, and it tends to have be prone to adversarial attacks. And what I mean by this is any type of perturbation when you add in like some false data really provides inconsistent solutions. So this isn't really good for us, and compartmented with not being able to even test whether your solution is correct or not is such a disadvantage. So what we try, a third aspect of this is it's very non-general. And what I mean by this is it's not very compartmentalized and it's not very modular in a way that it resembles a cookbook system, and where you go from training a data, you add a lot of layers, you forward prop, backward prop, and it has a fixed definition of the layers as well as the solver that you can't change, which you have to apply from forward and backward propagation. So with all three of these, the traditional way of applying deep learning neural network is really a disadvantage. So let me talk about one in particular, and one of those is the concept of defining the layers. So with traditional deep learning, you usually stack, as I said, these layers to get a very accurate solution, especially when you have and this requires a lot of training data. Altogether, increases the computational time. And by means of using an explicit layer, it's really not so efficient. So therefore, we need to define another type of layer called the implicit layer. And this implicit layer, what it allows us to do is, instead of specifying how to compute the layer's output from the input, one would need to specify the conditions required for the layer's output to satisfy. In layman's terms, these conditions often resemble a constraint problem where you have an objective function that it has to be optimized. In other words, you have to solve for a root. So one of the advantages of using an implicit layer is that by introducing this generality to a neural network, you can modularize and separate the solution procedure of the layer from the definition of the layer itself. And using this approach for defining the layers, it's really easy then now to approximate and to solve the differential equation. As we'll see that you can use different types of solvers instead of just using one, and you can use not just a stochastic gradient descent, but you can actually use Runge-Kutta, Atom, or any type of solver that you know in your typical numerical analysis class. And besides just the flexibility of changing out a solver, you also have the ability to vary step size. And when you vary the step size, this gives you some allowance for reducing the computational time. So relating and other ways of that this implicit layer can really revolutionize the neural network schemes is that it can reduce the memory costs. And what I mean by this is, when compared to a traditional neural network, the use typically uses automatic differentiation when you're doing the forward and backward propagation. And by this leads to storing the computation and graph for the complete solution procedure, along with all the temporary iterative values stored for each solution. Why this becomes a disadvantage is because the excessive amount of information actually has high memory costs, which is why altogether, as you guys know, deep neural networks are computationally expensive to train. So compared to a implicit layer, what ends up happening is we can actually directly compute the gradients of the solution point, which then avoids the intermediate variables to being stored, which ultimately reduces the memory consumption and increases the numerical accuracy. So altogether now, with that, the machine learning, the math, and the deep learning concepts provided, let's actually talk about the neural ordinary differential equation concept and all the advantages and disadvantages of it. So instead of specifying a discrete sequence of hidden layers, neural ordinary differential equations actually, what ends up happening is it parameterizes the derivative of the hidden state of the neural network, at which the output of the network is computed using adaptive neural network solvers. So the product of this is that these neural networks produce then not a discrete but continuous depth and continuous time models that ultimately reduce the memory costs and gives you adaptive evaluation strategies, but that varies the time steps as well as the number of layers according to an error tolerance. And by trading off numerical precision due to this accepted tolerance, we're able to reduce the speed of our neural network. So with that, let me just show you guys some pics that will kind of enroll with our implementation. But one of the advantages, as I mentioned, is if you compare this left picture, which is just like our typical residual neural network, with the neural ordinary differential equations, you can see that the traditional neural network has a fixed amount of depth. So the dots that you see here is fixed throughout, depending on the input, hidden, or output layers. But when you compare this to a ordinary differential neural network, you can see that these different dots actually vary depending on the heuristics of each of the layers, depending on whenever you need to use it. So it really optimizes and reduces the memory as well as the computational time. And not only that, as you can see, not with just a 1D data set here, but with a two-dimensional nonlinear data set, it's very robust. As I mentioned, any type of perturbation doesn't affect it, and it's not prone to overfitting. And you'll find out in the end that it actually provides a fair accuracy. So with that, what we're going to cover here today is somewhat twofold. First, I'll talk about the mathematics definitions that is underlying the this ordinary differential equation network, and then we'll end it with some implementation. So first of all, what I'm going to try to define here is the concept of cost function, and also the how we can create the classifier. And with that, well, this leads us to providing a contrast between a static control versus a dynamic control neural network. Mainly, this classic static control neural network is associated with our traditional residual neural network, while the dynamic control is more for the ordinary differential equation, which has more of the time component, as I mentioned. And then we'll kind of define what it means to do a forward propagation. And forward propagation is very, as you can see, is tied to the residual neural network, where we are trying to solve, in our case, a first ordinary differential equation. And in the end, we'll compute the outputs or the weights and bias parameters and the loss function. In order to get the underlying hidden state, we need to perform a backward propagation. And for an ordinary differential equation neural network, the means of doing this is through a variational and a joint minimization control that allows us to calculate the gradients of the loss function. And when we minimize it, we'll be able to find the hidden state of our equation. And the way of doing this is very easy. It's not like this traditional neural network, as I mentioned. All you have to do is to change the sign of your function, and not so much. You don't have to you don't have to meet an invertible matrix, and because it's a continuous function rather than a discrete function. So that's one of the advantages of this. Again, how we're going to derive the system of ordinary differential equation is we're going to create this Hamiltonian system boundary value problem, which has an initial condition, boundary conditions that we have to satisfy in our optimized objective function. And then by combining our variation and a joint Hamiltonian system, and this leads to this underlying concept of first order necessary conditions that needs to be satisfied for our optimal property to be to have this optimal property. And what this ensures, as I mentioned, it gives us an a priori analysis component where we can query whether our solution has consistency and convergence. And it gives us a robust way of analyzing and minimizing the sensitivity of the network so that it's not prone to any adverse attacks, as well as or a perturbation of the data set. So by that, after we differentiate the network, we're gonna have to integrate in order to actually solve for the parameters in our backward propagation, and we do this through this solver, the Rangakata numerical scheme, which is easily implemented, but it has a fast convergence. And with that, in order to actually maintain this optimality property in the discrete case rather than in the continuous case, we're going to have to use a partition symplectic Rangakata numerical scheme by fixing a parameter through all the layers. I'll explain that in a little bit, but I just want to say that again, one of the ways that makes this neural ordinary differential equation method really attractive is the ability to swap out any type of solver that you want. Either you can use a simplified Rangakata, which is an Euler method, or any of the adaptive stepping numerical solvers that you already know, so that in traditional neural networks, such as stochastic gradient descent, root mean squared prop, or ADAM or ADGRADE. So with that, let's kind of move on to the first definition here. So just to talk about it, so this is a typical cost function that we're trying to minimize for a neural network. And once we do this, we parameterize it and then get a classifier. So for a regression type of problem, your cost function will resemble a squared cost function. But then for a classifying type of problem, it most likely will resemble a cross entropy cost function, as you can see here. And this is just a comparison between having a discrete classifier versus a continuous classifier. For the most part, for our case, we're going to be using this continuous classifier. And then now let's move on to actually defining a general neural network static, minimizing control, constraint, and activation functions, which will be important for us. So as I said, in this, when we're talking about an ordered differential equation, we're going to be solving an optimization problem where we're going to have the objective function, which we're trying to minimize, as well as constraint. In our case, for a neural network, this constraint actually resembles the forward propagation that is typically done already, and you guys are well known of it in the residual neural network. And we also have this activation function. And just in layman's terms, what is an activation function? This is just maps the inputs to the output, and this can be a tangent, ReLU, and this or softmax. There's so many different ones that you can use. And then to relate the static neural network minimizing control to a more of a continuous sense, where you have a time component, this will be what you call the dynamic version of that. And the only difference between this and this is then you have this time component, as I mentioned, this total time, and then this time derivative in the constraint. So with that, let's move on to, so that was all forward propagation. Let's move on to how do you do a backward propagation for our ordinary differential equation neural network. And one of the first things that we need to understand is how do we define this variational minimization control. So how we do that is, as we've defined the time version of the neural network minimization control, all we have to do is just remove the implied index and summation over the number of data points, which gives us this variational form. And as you can see here, this variational neural network actually has this Jacobian in terms of with respect to the to our hidden state here. And as I said, we're going to have a derivative throughout time here, because then this gives us more of a dynamic sense. And then I think more important than that is turning it into the adjoint minimization control. And this adjoint problem here is actually the main concept of how the backward propagation is done to the neural ordinary differential equation. In a way, this is the backward propagation. So how we define this is we have an adjoint variable pt that this is being multiplied to the, and then by using integration by parts, we then find that this is the form of this adjoint neural network minimization, and we do this both for the minimization objective as well as for the constraint. And then with that, to form the boundary value problem or the ordinary differential equation for our neural network, we need to use a Hamiltonian system here. And this is the final form. You can look at the others, but mainly this is what we're going to be solving for our differential equation. And then this leads us, by combining the variational and then the adjoint as well as for the Hamiltonian system, this leads us to the first order necessary condition that we need to satisfy in order to get the instability property. And again, what this does for us is it ensures consistent convergence of the solutions, and it minimizes sensitivity of the network to perturbations of the inputs. And this is where we get the boundary conditions and altogether the optimality property. So after we do the differentiation, now we have to discretize, because then when you're doing backward propagation, there is no analytical way of actually computing this. So this is where the geometric numerical integration comes in when we finally time discretize the minimization problem. So in here, we have a Runge-Kutta parameter. As I mentioned, this is going to be the adaptive solver that we're going to be use, because it provides the maximum convergence. And then from here, we discretize the forward prop, as well as now what we're trying to do here is instead of using the full Runge-Kutta method, we have to turn this into a symplectic partition Runge-Kutta. And why we want to do this is so that we can preserve the quadratic invariant, and using the geometric numerical integration, we're preserving the structure. And how we can do this is we just have to fix one Rank-order parameter and use it throughout all the layers. And these are all the equations for that. And then I've kind of labeled which is one for the forward propagation as well for backward propagation. And then in order to simplify Rank-order methods, sometimes second, fourth order, it may be very computationally expensive. We can obviously swap out an Euler, explicit Euler forward or an implicit Euler method for the time discretization. And to make it even more simpler, we kind of swap out this gradient and cost function, as talked about the cost function here. And then from there, we just apply this gradient and we swap out this gradient cost function for the backward propagation here. And then in the end, this differential 314 and 315, these are just the two different versions of what we're going to be implementing subsequently for the typical residual neural network, optimal control with the Euler method applied, as well as the neural ordinary differential equation optimal control with this symplectic Euler method applied as well. I think the most important thing here, however, is just taking a look at the algorithm. After all the math I've talked about, let's move on to more of the computational science here, where, okay, what we're going to actually implement in the computer is first we initialize a guess for the parameters, and then using hyperparameter, then we can actually kind of tune the computational scheme here. And first, as always, we do a forward propagation. We compute the hidden state with the control parameters. And the hidden state, before what we're trying to get here are the weights and biases as well as the loss function, which is this L here. And then in the backward propagation, we try to find the hidden state by minimizing this loss function. So these are all the different components, as you can see. But what this picture is, and really graphically explains, is a very well thought out way of applying this neural ordinary differential scheme. Is so when we do with our initial state, we have to conduct a forward pass by finding out this feature here, and then this gives us the loss function. And then in the backward propagation, as I mentioned, you have to do an adjoint method. Here, you have to solve another ODE. From here, you can find the underlying state, hidden state of your system, and by the combination of the forward pass as well as the backward pass, you can then find the embedding of your data set and classify or use this for regression. So with all the mathematical concepts behind us, let's actually now move on to implementation. And I think before we even do this, let me just talk about briefly about the existing packages that are available for us. And what's great about this is I'm actually going to apply this both in Python as well as Matlab. And I hope you guys really enjoy the concept as it gets implemented here. And so for Python, there's really three types of packages that are commonly used in the industry that's really applying this novel ordinary differential equation neural network. And these are the torch depth equation here, as well as this is just kind of like PyTorch for differential equations. And we have JAX here, which this is the one that we're going to be using for this implementation. And we also have another similar kind of like a PyTorch, but torch dynamics. I think torch differential equation and torch dynamics are really great. But the reason why we want to use JAX is it has this feature called VMAP, where it really implements and trains the neural network simultaneously with our underlying dynamics, which is one of the reasons why we're trying to do this is to reduce the computational costs. And for Matlab, you're going to see that we're going to be using a linear algebra and a calculus packages. And really, why I got attracted with this type of neural network is because now I can really use other mathematical constructs and just build this neural network from scratch. And you don't actually have to rely on like prepackaged Python neural network like Keras or PyTorch or TensorFlow, which you can do. It would be good to validate this type of neural network scheme using those packages. But for me, it's always good to have this verifiable mathematical construct as well as just the underlying concepts for implementing such a machine learning algorithm. So what we're going to be using in Python is going to be more of like kind of like just an exploratory, kind of give you guys a flavor for how the concepts and how to implement this in a very, I would say it's a skeletal, but it does give you the main concepts, and that's very important. I mean, it's very simple, and what we're going to try to apply it is to a one-dimensional data regression. And then after we understand the concepts, then we're going to extend this, involve it to Matlab, where it's going to be a two-dimensional data set, and in this case, we're going to be using it for classification. Okay, so for this first case study, as I mentioned, it's going to be a one-dimensional data regression in Python. And then what we're going to compare are the performance of residual neural network versus the new ordinary differential equation regression. And so I'm going to call this RNNR, and then the one that we're most interested in is NODER. And what the basis of this, design basis of this data analysis that we're going to perform is we're going to define a regression predictive scheme. And using this one-dimensional synthetic data, which I'm going to show you guys in a bit. And what we're trying to do is we're going to predict this function that is this underlying synthetic data that I'm going to form by mapping the inputs to the target function value. And the objective is to predict the function value for the data set by fitting a training data using both the RNNR and then the NODER. So, and then how we're going to assess the performance is using this testing data that's compared with the predicted data, qualitatively using the root mean squared error, and also comparing the data visualization qualitatively for the function value. And so the very first step here is with any Python notebook is to just import the dependencies. And like I mentioned, we're going to be using JAX. JAX has NumPy in it, as well as it actually has its modules for neural networks, which will also be used. And another thing here is I could have written this on my own, but I just use scikit-learn metric, mean squared error, for simplicity. So the second step here is to generate a synthetic data, and it's a tan function. I could have used another function here, but we'll just use this type of function. The reason why I generated all these points, I think there's like 50 input and target points here, is so that I can actually compare this to the number of layers that I'm gonna so we can have a one-to-one mapping between the numerical versus this true value. So the third step here is to define the regression neural network regression. What you can see here is first, we're going to set up the functions for this deep neural network using this MLP function. This MLP function is really just a way for us to compose the layers. And then this set of functions that you see for the ResNet is just, this first function is using this MLP to compose all the different networks. And then obviously for what we're trying to minimize here is our loss function. Since it's a regression, we'll be using squared loss. And then in order to train our function, we're going to be using this random parameter definition. And in order to predict, we're going to be using this optimizer to reduce the squared loss here. So with that, again, we're going to generate a synthetic data set to randomize the function. And then we're going to define our hyperparameters. And this is, if you wanted to play around with this, I included this in appendix. But mainly to explain some of this, what we're trying to do here, 1.12.1, is we have one input layer, 12 hidden layers, and one output layer. And what you can change here, as you can see in our parametric study subsequently, is as you change the hidden layers, you're going to increase or decrease your RMC depending if you're overfitting or reducing the error. And then this parametric scale, you can technically scale your data outputs, but I just use one. You can obviously vary this depending on whatever output you want to get. But I think the more importantly, step size. As I mentioned, you can vary the step size of your system, and this gives you, it's kind of like a learning rate. Reduce this, gives you steps you throughout dynamically. Reducing it will give you more accurate results. And then your training or number of iterations, we stick to 5,000. This could vary, but depending if you're trying to parameterize your function here, you can either increase this and see if your error will decrease. And then with a residual neural network, as I mentioned, the depth and also as well as the number of layers is specified. And when you have such a large data, 50 data points is not really that large of a data. you probably have to increase this to 5 or 10, what have you. But for the most part, it's really just a black box. And then, so by specifying a number layer, it really, the more layers you have, the larger your neural network is, the longer your computational time will be. So this is where that depth is specified. So once you specify this, it doesn't change your forward and backward prop. And this is throughout all the layers. So like I said, it's specified, it doesn't get changed. And so once you do that, you apply your training and predicting, and then we finally get this after we plot it. So the green is your true data, and the blue is the numerical data from our model, the RNN R here. And as you can see, I mean, it's good, but as you're going to see later on that this does overfit. And right here in a very simple toy model, it really does embed the data pretty well. And sometimes you don't want that, and that's just a sign of overfitting. And this is what you can see here graphically, but we'll confirm it with our quantitative root mean squared metric as well. So now let's move on to how we define this noder or numerical ordinary differential equation regression model. So very similar, we're going to keep it consistent because we're trying to compare this. So, but the differences here is that in our setting up our equation for the functions to define our neural network. So as I said, this neural ordinary differential equation is a dynamic system. So we have to define the dynamics of it by specifying a state, time, and a parameter. So these are the main ones that you have to input for our dynamics. From here, you apply this customized function, which is just chaining an output of the base layers. So this dynamics here uses a base layer, and this base layer we'll be applying the ODE solver, which is a Ramacutta, which is in our package here for JAX. There's this really neat function called ODEINT, which is a built-in function, which you can the inputs of it is the defined dynamics of your neural network, as well as the input, the start and end times, as well as the parameter. And I think the most important parameter here is the absolute and the relative tolerance. As I mentioned, you don't specify the depth of the layer or of your neural network for all the layers. You specify tolerance and accepted tolerance, meaning the precision. And so it doesn't really, as you can see, you're not trying to predict the actual value, but kind of like a threshold of how far plus or minus off the true value. In this sense, you're trying to trade off precision with lowering the amount of speed. Because if you want to predict it exactly, it might take a while. But then again, you need to have a lot more layers if you're going to use residual. In this case, you're trying to meet it only to the point of a tolerance so that you can reduce the error as well as reduce the computation time. So our loss function here, very similar. We're going to be using a square loss function. But I just want to say that we're going to be batching the ODNet. I mean, this just means that we're gonna stack it. It reduces the computation time again. And very similar, we're going to train our model using this randomized parameters, and then we're going to update using the optimizer here to predict. Again, so we generate the synthetic data, and then we define our hyperparameters. The only thing that's missing here is everything's the same, except for the depth. So there's no depth because the depth is varied. The number of layers is varied depending on the tolerance. And I think that's something that I want you guys to really get, is that the depth varies depending on the tolerance, and it really does get optimized here. You won't really, we're not going to compare it in the 1D case, the time, computation time, and then we'll do it in the 2D case, and you're going to see that it really does, in fact, converge really fast, as well as produce accurate results. And so just to give you guys a pictorial of how it looks like in the end after you graph it. So as you can see, it's very good, very accurate graphically. It doesn't overfit. It does, it embed the natural pattern of the data set, but not fully get the characteristics. And that's what we want. We don't want it to be exact because that's evident of overfitting. So looking at these two neural network algorithms, let's actually, instead of just using a graphic or qualitative data visualization, let's compare it numerically using a quantitative metric, the RMC, or the root mean squared error. So what we're going to do here is a parametric study. What I try to run here is I'm going to increase the parametric study is going to be specific for the number of hidden layers. So we're going to vary the number of hidden layers for the neural network for both the the residual neural network and then the ODE neural network. And we're going to vary it from 1, 5, 10 to 15 layers and see how it affects the root mean squared error as well as how the qualitatively how the graph looks, and see if there's any overfitting and how the errors change. So for the one, I'm not going to explain each one because I already explained it, but for the one layer case, as you can see, the RMC SE here for the residual neural network is a little bit, it's actually high for both of these. So what we want to try to do is we want to try to minimize this. In the one layer case, it's not really dependable. For the most part, a higher RMSE value means that it's more it's more of an error, and what you want to minimize this value so that you get less error, more accurate solutions. So in this case, it's not really dependable, and as you can see, even the graph itself tells you that the solution isn't really dependable. So let's look at the next number, which is 5. So for 5, see, there's more dependable now. So for the ODE neural network, you have a lower RMSE than the original neural network, which means that it's more accurate. And as you can see data visually here, it kind of seems like the neural network in blue here, reduced neural network in blue here, seems to have lesser error, but then the red, which is the ODE neural network, but then again, as I said, this is inherent of overfitting when you really go one-to-one with the data instead of actually just getting its general general behavior. So let's move on to 10 layers. So this is for the 10 layers, and then now for the last 15 layers. So as you can see, when you compare the RMSE throughout the evolution of the number of layers, we actually started to get more accurate results for this. So the RMSE here, as you can see, it actually increased, and then for the residual neural network, but it decreased for the ODE neural network. So when you have an increase in RMSE, that means it overfits, and when you have a decrease in RMSE, that means it's accurate. And so in this case, that's how I confirm that using just a typical residual neural network is really prone to overfitting. But when you're using this ODE neural network, it converges really fast, 10 layers, and also it doesn't overfit. So now let's actually talk about just some of the underlying insights that we gained from this first case study. So one in particular is that the ODE neural network provided more accurate results than the residual neural network in terms of regression. The reason for that is the root mean squared error was lower for all the number of layers except for the first hidden layer, of course. And oftentimes that doesn't really give us the best results, and so that's why we're doing a parametric study, increasing the number of hidden layers. Typically, increasing the number of layers, as I mentioned, leads to lesser error with more accurate results. This was only confirmed with the numerical, with the ODE neural network, whereas in the original neural network, the error increased as the number of layers increase. And the reason for this is it learned the heuristics or the underlying embedding of the data by perfectly aligning it one-to-one with the embedding. With that, it's notable to state that the original neural network regression is more prone to overfitting than the ODE neural network regression. That makes it more sensitive to hyperparameters. So to resolve this, a suggestion for a future study would be to perform a hyperparameter tuning, maybe reduce, because at the 5 layer it was already overfitting. So maybe kind of reduce the step size, or reduce the hidden, or increase the amount of hidden layers in between 1 to 5, as well as like increase the iterations, and to see if there's any difference between the root mean squared and then also the data visualization. So with that, let's move on to the two-dimensional case, and then we're going to be using Matlab here. Actually, this should be Matlab. So with that, so here, instead of just comparing this to two types of algorithms, we're going to be comparing this to 4 types of algorithms. And so you're going to get the full the full plate here with the neural network classification, residual neural network classification, as well as the neural ordinary differential equation classification, as well as a neural ordinary differential equation with a simplex feature. And then the difference, just to talk about the description for these, the neural network classification here is just your typical like convolutional neural network versus this residual neural network, which we already talked about. And the difference between this neural ordinary, this first one right here versus this with the simplex applied, is that it allows us to actually make it affects the time steps. So at the time steps, it doesn't matter. We can zero it out and makes it sparse. So zero time step means it's sparse. The more sparse the time steps, the more reduction to computational time, and more memory costs reduced. And so for this neural network compared to the original network, you're going to see that this is actually a little bit faster. And even the original network does converge as well, pretty quickly as well. You're going to see that having an optimized time steps will actually reduce the original network computational time as well. So with what we're trying to do, just to talk about the design basis again, the objective is to classify the data set by fitting the training data with all 4 of these algorithms. And what we're trying to define is a classification predictive scheme. And this predictive decision boundary, and mainly it's a linear system. I'll show you guys in a bit. Sometimes you can apply this to maybe more like a nonlinear set, but for this one, we'll just keep it simple. But for this decision boundary, we're going to try to separate the color-coded points in our 2D data set to target value, function value, or area. And what I mean by this is, so when you have blue or red, then when in the data set that's randomized, this decision value will have a class for blue and a class for red that's separated by the boundary. And the point of this is to classify them in the end by separating the blue and the red points by learning from the data. So with that, I'm not gonna show you guys the actual code. You can refer to it in the appendix. It's such a long code. I'll just talk about the theory as well as the concepts and the results. So in our first step, we don't have to really import any dependencies, because in Matlab typically everything is already there when you download it outside of the program. So what we'll do is we'll just talk about the second step mainly, which is just to create the data. So in this plot, when we plot the data, we had like 5 different choices here. For simplicity, I just chose one, which is the spiral 2D data dimension, and then the number of data points here is 2,000 points, just to make it more robust, more complicated and complex. And so to show you guys how that looks, it looks like the spiral as I mentioned here. So as I mentioned, it's going to be a randomized feature with different types of points for red as well as for blue. And then the point here is to classify this into a decision boundary. As you can see, as an example here, is once we plot this decision boundary, the points after we train the neural network should be able to classify the points in the blue region as well as the red region. And then so the same way with the one-dimensional case in Python, here in Matlab, we're going to do a parametric study of the number of hidden layers, and we're going to choose 1, 5, 10, 50, 100, and 500 layers. And here it's the concept is pretty much the same. We're going to try to observe qualitatively and quantitatively how the performance of these different layers compare. And so I'll just show you guys some of the different. So first one here is for the one layer, but this is mainly for just a typical neural network. And then this for the one layer residual neural network, and then this for the one layer neural ordinary differential equation one, just the ordinary one. And then this one is with the simplex, that means with the sparse time steps. And as you can see, the original network doesn't really contrast with the neural network with neural ordinary differential equations here, but there is slightly a difference between the one with the simplex versus the one without. As you can see, in the end, these two, the residual neural network as well as the typical neural ordinary differential equation, actually are the ones that fairly perform well. So just to skip through this, you can review this in your own leisure. But just to go to the parametric study results, I won't cover this as much, but just to show you guys one specific case. So for the accuracy, this is for the one layer. It's probably not the most. I'll skip to the one with the 500 layers to give you guys the full load. But mainly, what you're gonna see is, so you have this accuracy metric, which as we increase the number of iterations, and what you're gonna see is you're supposed to get this converging at a particular accuracy, and once you see that, then that's going to be your final accuracy for that neural network. And then for the next type of metric, we also have the function value, and this just allows us to see what value that this our neural network converges in the end. Often the case, these should converge to roughly the same value. If it doesn't, that means there's something wrong or some overfitting. As you can see, it's roughly the same value, and then it seems like the blue case here typically is overfitting, it has some error. And then also the other type of metric is the time step size. So this time step size, it's easier to see with this one for the 10 layers. Is as you can see, the green here is the one with the simplex, and simplex here allows you to have sparse time steps for the cases that are where you're not analyzing as much, and this allows us to reduce the time and memory cost as well as the computational time. And then for the regular ordinary differential equation network here, it does vary throughout, which also it's not as good as the simplex, but it does give a fair performance. And then for the other ones that doesn't have this feature, your time step is going to be constant, which means that that it's utilizing and it's not optimizing the time steps, which would mean that the conversion isn't as fast. So just to give you the final word on each one of these, let's skip to the 500 layers for the accuracy and kind of give some insights to it. For the 500 layer, as you can see here, so the orange, the purple, and the yellow definitely has high accuracy, and the two that are the really good ones here are the yellow and the orange, which is depicted by the residual neural network as an ODE neural network. So that gives you 100% accuracy, which is really good. And then, but the simplex actually is kind of surprising. This one does converge, but it seems like at this 20,000 iterations, this is why I didn't say this, but we had 28,000 iterations here. It seems like this is still changing. So maybe if I increase this to 30,000, we'll get a plateau here. So maybe this is not the end of the story. But then the one thing that I want you guys to see is that this neural network here in blue, the typical neural network, this can be convolutional neural network, really doesn't give you a fair accuracy. It kind of plateaus at 50%, which is really bad. So this just tells you that your neural network is prone to overfitting. It doesn't give you an accurate solution. But if you use ResNet, or even better, the ODE net here, as you can see, the yellow converges really fast, faster than the orange, even faster than the purple. When you use ODE neural network, you'll have faster convergence, and you'll have high accuracy, and it's not prone to overfitting. So let's kind of confirm that with the function value. So with the function value here for 500 layers, what you're going to see is as you increase the number of iterations, this should converge to somewhat same solution. So as the orange and the yellow again, and the ones that are pretty much first and second with the highest accuracy, does converge to the same solution, which is very good. The one thing that I want you guys to see, however, is the ResNet here. Actually, so the dashed line is for the testing data, and the solid lines are for the neural network numerical predictions. There's a slight difference between the ResNet here, testing data, and the predictive data versus the for ODE net, which means that it is prone to overfitting, as we've seen in the 1D. So altogether, the best algorithm for this model is probably the ODE net, that without the simplex. But the simplex, you can see in our third metric that it does have its advantages as well. So let's move on to that one. So with the time step for the 500 layer time step metric, So this is the time step size, and then the number of time steps here. As you increase the number of layers, as you can see, for the ODE net and ODE net simplex, you're going to have varying. So for the ODE net regular, in the purple, you're going to have varying time steps because it's getting optimized depending on the complexity of that layer. And then for the ODE simplex, you're going to see most of them are 0. It's sparse, which should reduce the computational time. And it's only increasing to the point where you need it, but to the point that you don't need it, it reduces it to 0. Very, very good in terms of computation. And then for the regular network as well as a residual neural network, which you can't really see here, but mainly it really does follow the same. It's at 0 here, as you can see, it's at 0. So with this, it doesn't. It's constant, which means that it's fully utilizing that time step, even though you don't need it. Which, in the end, conceptually, you can think that it will increase your computational time. So with that, let's actually provide some just some insights for the results for our second case study here. So with all these 4 algorithms, one of the ways that we can conclude is that the most accurate neural network model is the residual neural network as well as the ODE neural network without the simplex. And the reason why we can say this is because as the number of layers increase, the accuracy progresses to 100%, as you can see. And then, however, we can further observe that the ODE neural network converges relatively quicker than the residual neural network because it requires lesser iterations to reach 100% accuracy. And looking at the quantitative performance now, it seems that the regular neural network experience overfitting because as the number of layers increase, the accuracy decrease, which is evident of overfitting. And then for the one with the ODE neural network with the simplex, it also did quite well, even though it wasn't as well as the others in terms of accuracy. It didn't reach its maximum accuracy at the tested iteration that we specified, which is then allows me to believe that maybe we should have increased the number of iterations. And looking at the data visualization, as I showed you earlier, the accuracy of the classifications are consistent, where we see that there's more error associated with the typical neural network. And this means that there's more color-coded points that are incorrectly classified, and versus the other ones where the color-coded points are classified at the correct boundary or side of the boundary line. And examining the qualitative metric, what was observed is the accuracy metric is also consistent with the function value. For RNC and as the number of layers increase, the neural network converges roughly the same value. And for the simplex ODE neural network here, there's a slight % difference compared to the residual neural network as well as the regular ODE network. But then again, the value is still changing, so maybe I should have increased the number of iterations as I mentioned. And then for neural network, we also confirmed this quantitatively, where overfitting is observed where the value is somewhat consistent with the others up to 10 layers, but started decreasing as the number of layers increase. And looking at the time step size, as I just previously showed you, as the number of layers increase for the ODE neural network, more variation in step size, and then for the simplex case, more sparse time step size. This showed that we have lesser memory and computation. And as I showed you guys the convergence, this is in par with the convergence of the ODE neural network, which converge fastest of all the neural network here. So with that, I think that I really went over time here, but I hope that you guys enjoyed my presentation. And here are the references. And if you guys would like to check out these Python and Matlab code implementations, if you have further questions, please ask me or email me. Thank you so much and hope you have a good day.